presento el ponent, en Roger Samsó. En Roger Samsó és enginyer geòleg per la Universitat de Barcelona i doctor en enginyeria ambiental per la Universitat Politècnica de Catalunya. En Roger Samsó és, diguem-ne, conegut de la casa perquè va estar treballant aquí durant el projecte Medeas fins a l'ICM fins al 2019, l'any 2019. Actualment està treballant com a investigador al CREAF i és el que porta la recerca del projecte europeu Locomotion, que és de modelatge de la transició energètica a Europa. La seva especialitat, per al que ja he anat dient, és bàsicament els models i tot el que fa referència al modelat. Ell va començar amb models de dinàmica de fluids, qüestions, tractament d'aigües residuals, etc. I després ja amb el Medeas i amb el Locomotion està amb la part de models d'avaluació integrada de transició energètica. És membre del laboratori que tenim a la UB i al CREAF d'Energy and Earth Systems i és també un dels pares del model PAI-Medeas que es va desenvolupar en el projecte Medeas, el projecte europeu que van fer aquí a l'ICM. I de resultes de la recerca que ha vingut portant darrerament, el que us explicarà avui, ara ho introduirà, però és uns anàlisis que han fet independents de models, o sigui que hi ha tota l'altra part d'anàlisi de dades per complementar els models i en la qual també ha estat fent una feina molt rigorosa i molt interessant. Bé, no m'allargo més, us deixo amb el Roger i espero que us interessi la xerrada. Gràcies.
Bé, doncs, gràcies Jordi per la introducció i gràcies també al Ramon Massana i la gent de l'ICM en general per haver fet possible que pugui ser avui aquí. Us faré la xerrada en anglès, si no hi tenim cap inconvenient, perquè vaig veure ahir que està anunciada en anglès i per tant, per la gent, potser no vosaltres, però per la gent que estigui per internet potser els és més fàcil. So, as Jordi mentioned, the idea for today's presentation is to present the results of this study that we carried out, which has the same title that this presentation. And today I'm here, but this has been the work of 4 scientists, and these 3, I guess, some of which you already know because they've been here, they've worked here, and they still do, so some of them, they still do, so yeah. So as I mentioned, the objective of the presentation is to show you the results of this paper that we published a couple or 3 weeks ago. And the idea was to assess the potential of marine renewable energies and their potential contribution to the future energy mix. And in terms, evaluating this in terms of net energy, so the energy that actually reaches society. So yeah, the motivation, well, it's not a surprise, we're in an energy transition, so any source of renewable energy that we can gather in a sustainable way, of course, will be welcome. On land, we have strong competition for different land uses, so we need to produce food, we need to do all other human activities and also produce energy. So this takes a lot of land, and so people are starting to look, it's not recent, so for a long time people have started to look in the ocean as a mean to produce renewable energy. It's important to know that 40% of the world population lives within 100 kilometers from the coast. So it is also important that the place where we produce the energy is not so far away from the place where we consume it or what it's demanded. So in this way we have less infrastructure, less transmission losses, and so on. And then there are regions, or especially islands, that do not have access to renewable energy, so this is a particularly interesting energy source for these regions. Why why do we need to study the potentials? Well, the main reason is to see how much or to what extent they can contribute to the future energy mix, so how much we can count on these energies for the future. Also, and very important, to understand the extent and the kinds of impacts that this sort of energy can bring to marine environments. And also, which is the reason why we started this work, is because the energy potential is generally used as input to integrated assessment models, which some of you may be familiar, are sort of models that allow to analyze socioeconomic systems, socioeconomic systems in a very holistic way, so taking into account all dimensions of societies. So that's the motivation. Now, a few concepts, 3 actually, that I want to explain in order for you to better understand this presentation. The first one is the energy potential. So the energy potential is actually how much energy we can get in a certain region and for a certain time frame. So for instance, how much solar energy is available in Catalonia for a year. That would be the idea behind this concept. And then we classify it in several degrees. So the theoretical potential would be the energy that is naturally available, so the energy of winds, how much wind energy there is in Catalonia or in any other region or in the world. Then, if we take into account technical constraints, we go to the technical potential, which is obviously smaller because with the current technologies we cannot exploit the whole energy that is available. Then if we take economic considerations into account, we can extract less energy. And finally, if we take sustainability into consideration, sustainability constraints, there's less energy available. So think of, for instance, hydropower. We cannot use the whole flow of the river to produce energy. We need to leave some ecological flow for the ecosystems to thrive. That's the first concept. Second concept is the energy return on investment, or la taxa de retorn energètic in Catalan. So it's the ratio between the energy that can be produced over the lifespan of an energy technology divided by the energy that is used to produce this energy. Okay? And finally, it's a very similar concept to the previous one. They are related with this equation. But the net energy is the difference between the energy that we can produce and the energy that is used to produce this energy. Okay? So once that's said, now I'll explain what we actually did in this work. So this work was based on 2 main bibliographical reviews, one for the global potentials of marine renewable energies for each of the different resources. And then we classified them according to whether they are theoretical, technical, economical, or sustainable. This is not always easy to do this classification because not always there's sufficient information to tell whether it's more theoretical or technical or economical or whatever. So the boundaries are not very clear. Then on the other side, we perform a bibliographical review of life cycle assessment studies available for the different technologies that gather marine energy. And through this bibliographic review, we looked for these parameters that you have here, so the lifespan of the system, the capacity factor, cumulative energy demand, so how much energy is used to produce this energy, and also the device power rating, what's the power that can be produced with this device. And with this, we obtained the EROI, and I'll go back. So here in this equation of the EROI, you have all the parameters that I showed you. So the device power rating, the number of hours per year, the capacity factor, lifespan, and then divided by the cumulative energy demand. And based on this value of the ROI and on the potential, through this equation, we obtain the net energy potential, which is finally what we want to what we want to assess, how much energy surplus can we obtain with marine renewable energies. Now here's the body of the results. There's a lot of them, but don't worry because I'll summarize a bit. For instance, well, just to mention that we are looking into the energy of tides, waves, thermal gradients, offshore wind, salinity gradients, and ocean currents. Okay? But as I was mentioning, we will only cover the first four because for salinity gradients, we also analyzed the potentials and the ROI, but we found that the current ROI of this technology is very low, so it means that it's it has a very low energy efficiency, so currently it's not in a viable state, so we will not cover that. And the energy of ocean currents, we also analyzed it, but we found that there's literally no data available to assess this type of energy potential. Actually, by ocean currents, if I may zoom in here, we mean the currents that occur on the eastern boundaries of the continents that are caused by the drag of wind and also by density gradients produced by temperature and salinity differences in the ocean. Okay. So, yeah, I forget about these two, and I'll focus on tidal energy, waves, thermal gradients, and offshore wind. So, starting with tidal energy, there are two ways in which we can exploit tidal energy. The first one is by using the head differences between low tides and high tides. So in a very similar way that we do with hydropower, we use this energy, this potential energy to turn a turbine, let's say. This is called tidal range. And then there's tidal stream, which actually uses the kinetic energy of the currents that go up and down, and to move a turbine as well, and to produce, to use this kinetic energy. Focusing on tidal range, there are also two types. There's the tidal barrage systems, which is more established. The first system was built in France in 1966, and it has been operating ever since. And the other one is in Korea, and it was built in 2011. So there's a lot of experience in operating these kinds of systems. And I must say that these two systems add to 90% of the total capacity installed for marine renewable energies, not taking into account offshore wind, which is another. It's actually not oceanic energy. It's marine energy, but not oceanic energy. So yeah, these two systems have 90% of the capacity of all marine renewable energies, which is quite significant. And how this works, sorry, I went back. So in the left image, actually I'll zoom out. In the left image, you can see that you have this barrage, or this dam, actually, that you put in an estuary. And then when the tides go up, you close the gate, this gate here. You close this gate, you wait for the tides to go up, and when it's up, you have this gradient, this head difference, and then you open the gate and let the water go through and produce energy by a turbine. And the other way around, when you have the level inside your basin, which is high, you close the gate, you let the tide in the ocean to go down, and when it's at the lowest point, you open the gate and you produce this energy. Now, for tidal lagoons, there have been many projects, especially in the UK, for this type of systems, and it's just, well, this sort of structure, so building, the principle is the same, but it doesn't need to be in an estuary, it can be in the coast. You build these structures and the functioning is the same. There are projects since 2007, if I'm not wrong, but they have never become a reality. So it seems unlikely that they will ever do, because it's not the topic of this presentation, but, well, it actually is, but the environmental impacts of these kind of systems, you can imagine, it's very, very high. And then for tidal currents, the function is relatively simple. So you put these horizontal axis turbines or vertical axis turbines where the currents occur, and then you get this kinetic energy. And there are also other systems. I only put 3 here, but there are others. And this one here in the middle is the tidal kite, which is sort of a plane that makes this movement like this. It has some rotors, and with these rotors, the energy is produced. Talking about the resource. So yeah, the highest tidal range occur in these regions that you see here in red, so in the west and east coast of Canada. Actually, this got cut. Yeah. In the east coast of Canada, in the UK, France, also Portugal, in regions of south of Argentina, so in Madagascar or near Madagascar. And just to give you an idea of the range of these tidal differences, the highest tide in the world occurs in the Fundy Bay in Nova Scotia, and it's 16 meters between low tide and high tide, so it's quite a thing. And now, already looking at the results that we obtained in this paper, so in this table what I'm showing is the values that we found in the literature for the theoretical, technological, economic, and sustainable potential. As you can tell, there are not many studies analyzing the economical and sustainable potentials for marine renewable energies, and in particular, in this case, for tidal energy. And in this case, I also separated the studies that study all forms of tidal energy together, and those that focus exclusively on tidal stream and on tidal range. And here, by potential, I mean the terawatt hour that could produce in a year. So the first value, this 14,000 or almost 15,000 terawatts, corresponds to the energy that is dissipated by tides in continental shelves and shallow oceans. So it's about 1.7 terawatts. And then you can tell when we go from theoretical to technological, the values go significantly lower. And then we got also tidal stream, one study that focused on tidal stream, and you can see that it goes from this 4,380, which is 0.5 terawatts, to this 177 terawatts hour per year. And they generally say that, or it's generally said in the literature, that tidal stream has more potential than tidal range, because tidal range needs to be built in estuaries and in very constrained areas. So if tidal stream only produces 177, in theory tidal range should be smaller, although there's no assessment to date about this potential. Now, looking at the EROIs, here I divided it in 2 separate tables. The one on top is the tidal range EROI, and the values range slightly above 20. So for each energy unit that we invest in producing this energy, we produce 20. So it's quite efficient in terms of energy production. And then, if we look at tidal stream, the table at the bottom, the values are not so high, so they are around 9, 11, 14, 16, but still, they are still quite high. That was tidal energy, and now we look at the energy of waves. Here, there are plenty of devices that have been designed to capture the energy of the waves. I just show a few of them very rapidly. So we have point absorbers, which are actually buoys that are on the surface. and they are attached to the bottom, and through the movement, the vertical movement, they produce this energy. Then we have the attenuators, which is the image in the middle, and these are sort of snakes that also float in the ocean, that are attached also at the bottom, and it's through the relative movement between the different segments of this snake that the energy is produced. There's vertical movement and also horizontal movement that is producing energy. Then there's these overtopping devices. Well, for the first one, if you saw the banner of my presentation, what I was showing was this device here, which is known as Pelamis. It doesn't exist anymore. Nobody builds it. But yeah, it was one of these kind. Then we have the wave overtopping reservoirs. So an example of this is the Wave Dragon. It's a device which has this shape, and it has two arms. It's also floating on the surface. And when the waves come, these arms concentrate the energy of the waves, and the wave escalates through a slope. And when it escalates, it overtops and passes through the turbines, and it's there where the energy is produced. And there's also these devices that I saw that in Scotland there's one of the one at the bottom left, sorry. So in this case, it's an oscillating water column, and what actually happens here is there's this structure, and then there's the waves coming, and when the wave goes up in this structure below, it pushes the air, it increases the pressure, and this pressurized air is what makes the turbine spin. And the other way around, when the wave goes back down, when it retreats, it generates a negative pressure, which also moves the turbine in the opposite direction. And then, well, there are many more, but I'll leave it here. In terms of resource, what I'm representing here is the mean power of the wavefront. And you can see in red colors, it's where most of the power can be extracted. Well, where most of the power is available, actually. And it's in the North Atlantic, and in the Indian Ocean as well, and in the Pacific, in the North and South Pacific. So this is where the resource, or most of the resource, is available. Now, for wave energy, what we saw when we started looking in the literature is that, again, well, in this table I'm showing global potentials, technical, economical, and sustainable. What we saw when looking at the potentials for wave energy is that the uncertainty of the values reported was huge. So it went from 1 terawatt to 10 terawatts. So it's these 80 to 80,000 terawatts that you see on top. Then when they started using ocean models, they reduced this uncertainty, they went down, to 29,000 terawatts. But with these initial models, they didn't consider the direction of the waves. So when they went to the next step, when they included the energy of the waves, the potential decreased and is around these 18,000 terawatts. The last study considers only water depth up to 10 meters. So that's why it's a bit smaller. And then when looking at what could be obtained with the available technology, these potentials go much lower. There's actually an outlier, the 17,000. I'm sorry because they told me not to move, so I cannot go there, and I need to be here. So I was thinking I could do that, but not. So the one at the bottom is actually an outlier because it takes into account technical factors, but it looks more like a theoretical potential than actually what could be extracted with current technologies. So that's for the potentials. And then for the ROIs, we have reviewed a diversity of different technologies. So they are not comparable. The values given here are not comparable to one another because they correspond to different technologies. But what we can expect is that only the most efficient or the most energy efficient technologies are those that will end up in the market. That's what should be expected. And in this case, the values range from 6, 7, 8, and there are a few ones which are much higher, around 20 or 25. So we think that those are the ones that will make it into the market in the end. And now for ocean thermal energy conversion, if you were wondering what that stands for. In terms of technology, so here there's a working fluid with a low boiling point that is circulating around here, actually in this direction. And then there's water that's being pumped from the bottom of the ocean, which is cold, of course, and water that's being pumped from the surface of the ocean, which is hot. So when the fluid circulates, the working fluid circulates through this circuit, it reaches this heat exchanger here, which has the hot water coming, and so the working fluid evaporates. When it evaporates, it makes this turbine steam, and a generator produces energy. And then the working fluid goes down, and in contact with the cold water, it condensates, and it goes over and over. So this is why it is said that this is a baseload technology, because it can produce at any time, in theory, and this is one of the interests of this technology. This is a picture of the first system of this kind that was installed. This is in Hawaii. And well, you see a palm tree next to it, so it's a huge system. And this system actually produces energy for 120 households. So you can imagine the energy efficiency of this kind of systems. You will see later when I show you the ROIs. So this is the resource that is available. So it's in tropical and subtropical areas mainly. And yeah, well, when looking at the exclusive economic zone, which is 200 miles from the coast, of course, we reduce the locations where this could be exploited. Looking at the potentials, by considering an average temperature difference between the upper layers of the ocean and the bottom layers of 20 degrees, which is actually what is required to produce this kind of energy, and multiplying this by the whole surface of the ocean, they obtain a theoretical potential of 100 terawatts, which is gigantic. It's this 100,000 terawatts. And then after this rough appraisal, let's say, they started using models, and this study here, this corresponds to 1.7 terawatts. 2.7 terawatts. And in this study here, they used a one-dimensional model of the thermal structure of the ocean, and they also included equations to estimate how much power could this sort of technology produce. And yeah, as I mentioned, they obtained this 2.7. Then in a later study, which is the value at the right, they obtained this 43,000, which corresponds to 5 terawatts. And then successive studies have gone actually by the same team, so by the same authors, or mostly by the same, at least by the lead author. They went up as much as 30 terawatts. Then they increased the resolution of the model and they went down to 14 terawatts. So they kept updating these values with more or less success. The last study, the one at the bottom, in which they also evaluated the economical potential in the exclusive economic zones. They actually measured, so they used measured data to estimate this potential, which is within brackets, and this corresponds to roughly 8 terawatts. And also they modeled it, so they obtained it was published in Nature, I think, one of the journals of Nature. What's the problem here? The problem is that when we looked at the impacts of producing 5 terawatts with this technology, we found that the authors report that they need to pump 16 Sverdrups, so that's 16 million cubic meters per second, which is in the order of magnitude of the AMOC. So you guess it's not very feasible. And also Antonio García Olivares estimated that by pumping this much water from the deep layers of the ocean to the surface, which are loaded with dissolved CO2, we would be releasing 25% of the anthropogenic emissions of 2011. So, of course, it has a huge impact. The authors of these publications, they also mention that when they go up to 7 terawatts, they produce significant changes in the thermal structure of the ocean. So, in general, they recommend not to go above 2 terawatts, which is what we put here as the sustainable potential for this technology. In terms of EROI, well, you guessed it, so it's very low, so around 8. So it means that for each unit of energy that we use to produce the energy, we only get 8. So it's not very energy efficiency. Actually, in this work, we only considered technologies that have an EROI higher than 7, which is generally considered the minimum EROI for a society as complex as ours to function normally. So yeah, around 8, some report values of 5.9, 6.8. So the assumption that we made here is that only half of the resource, of the global resource, could be exploited with an EROI higher than 7, higher or equal than 7. And finally, for offshore wind, so offshore wind, currently there are 830 gigawatts of offshore wind capacity, and only 7% correspond to, of wind capacity, not offshore wind. So wind and land, offshore and land wind. So only 7% of this is offshore wind for the moment. There, at the beginning, only fixed bottom aerogenerators were possible, up to 60 meters of depth in the ocean. But more recently, they've started colonizing further depths with these floating systems. So the first, compared to the others, it's a mature technology because the first offshore wind farm was built in 1991 in Denmark, and the first floating system was built in 2009. So it's more recent, but still they have already quite a bit of experience. This is the map of the resource. So what I'm representing here is the capacity factor, which is actually an indicator of the quality and consistency of the winds. And of course, the darker colors represent more quality of wind, and the lighter colors represent less quality of wind. And then for the potentials, what we saw is that there are 3 main factors that affect the results that you see here. The first one is the depth at which they considered that these systems could be installed. So at the beginning, most of the literature only studied up to 50 meters because it was what was technically possible. And then right now they go up to 2,000 meters with the floating systems. So that was one factor. Then was the capacity factor, which is what I just showed you in the last slide. So it gives you an indication of the percentage of hours in a year that there are winds which are consistent enough to be able to be exploited. And the other one, the power density of the wind considered. So there are studies with atmospheric global circulation models that show that for offshore wind farms with in the order of hundreds of kilometers that take up hundreds of kilometers of ocean surface, the interferences between the turbines limit this power density to 1 watt per square meter. Other systems, which are not so large, can exploit higher energies up to 5 or 7 watts per square meter. But these are the three parameters that basically make up the differences that you see here. So the first value was lost during this value here is actually 73,000, not the value that we show here. This was edited in the text is correct, but in this table is not shown correctly. This actually measured the kinetic energy available below the atmospheric boundary layer, and it gives this 73,000. Then other studies, for instance, the one below is by Antonio García Olivares, and in this case they considered that the systems could be installed up to 225 meters of depth, but they considered this limitation in the power density. So they considered that a maximum of 1 watt per square meter. And they used different degrees of occupation of the continental platform of 10, 25, and 50%. So with 20, they got 15,000 terawatts, with 25, 39,000, and the rest with 77,000. Then the difference between this study of Antonio and this one is actually just or most importantly, the power density. In this case, they considered power densities of between 5 and 6, and they obtained these values also up to 200 meters deep. And then there's this study here, which is this one here. There are these 4 values here. And this one is interesting because the first 2 values correspond to depths up to 50 meters, so fixed in the bottom. And the next 2 correspond to up to 1,000 meters. And the first one of each 2 corresponds to scenarios of low occupation, because they consider 4% of occupation between 0 and 10 kilometers from the coast, 10% between these 10 and 50 kilometers, and then 40% from 50 kilometers to 200 kilometers. But you can guess that the higher occupation scenarios are even not, well, we didn't even consider them because it considers 80% occupation between 50 and 200 kilometers. So, yeah. And then these final studies, as I mentioned, these here, which give much higher values, are those that consider depths up to 2,000 meters. And then for the EROI, in this case, it's relatively, the variance is very low. So we have values from 33, 18, 12, well, you can make an average of this. And the average is around 20. Here, I gave you lots of tables, just a summary, and no need to look deeply on this table. Here, what I only wanted to mention is that for tidal range, we actually considered that the sustainable potential is as low as 0 because of the impacts. And a good sign of this is that since 1966, only 2 systems of this kind have been installed and no more. Although the EROI is very high, so it has an EROI of 20. Ocean currents, it's not included here because there's no data. And then salinity gradient, as I mentioned, we put technical potential of 0 because the EROI is very low. So this is what I wanted to show in this table. And here you have a summary of the values. Tidal range, waves, and offshore wind have a relatively high EROI. So it works, they are very efficient. Then we have tidal stream, which also have a reasonable EROI. And finally, we have ocean thermal energy conversion, which has an EROI around 7. For salinity gradient, we didn't put it because it was below 7, but we didn't know. Actually, there's a lot of uncertainty also in the available data. And then for the energy potential, which are in pink, we see, and also the net energy, we see that tidal stream has a very small potential, followed by waves, then it comes OTEC, and then much farther, there's an order of magnitude between these values and these values, we have offshore wind. And just to conclude, so what we've seen is that marine renewable energy sources could produce up to 57,000 terawatts hour per year, which is twofold the current electricity consumption globally, although this electricity consumption is expected to increase by 50% around 2050. 90% of these 57,000 terawatts come from offshore wind, which is a significant proportion. And then by excluding offshore wind, by only taking into account oceanic technologies, we could potentially produce up to 6,000 terawatts, which is a fourth of the current electricity consumption. Considering all these technologies that I mentioned today, the average ROI of the system would be around 20, but when excluding offshore wind, it goes down to around 8, so significantly lower. Of course, the results that we presented in this study are upper boundaries, because as you've seen in the tables, in most cases, we haven't considered economic or sustainability constraints, because there was no data available. Again, the values reported in the literature have high uncertainty, so I mean, what we provide here is an order of magnitude, and more research is needed. And final point, because here we're not at all advocating for marine renewable energy, but what we want to show is that we still don't know what the impacts of these technologies, the environmental impacts of these technologies may be, because they have not been studied. So we think that in this situation, the precautionary principle should prevail. So before deploying this in large scale, so environmental impact assessment should be carried out to prevent potential damages. So that was it, 40 minutes. And now if you have questions, I'll be happy.
Preguntes? Questions?
Poden ser en català, en castellà o...
Okay, thank you very much for your information. It was very interesting. Can you tell, please, your personal opinion on such problem as mechanical stability of offshore systems and open sea systems? Because it may be, maybe it is dangerous to put very high complicated equipment at the open sea. Thank you.
Okay, this was actually not the topic of this study, but indeed we've seen through the literature that most of these technologies have high maintenance costs precisely due to the harsh conditions in the open ocean. So that also increases or reduces the ROI of these systems, because they need a lot of maintenance. And also, since they are offshore, you need boats that also consume energy and so on. And in terms of offshore wind, I mean, I have no particular idea of how they may resist the offshore conditions. I don't know, maybe Jordi, if you want to add something.
Yeah, no, basically the problem is that one thing it's, for me, the problem is that there are two points. First, the technology at prototype. Okay, so we can assess what happens with that prototypes. And in fact, for instance, for offshore wind, there are some prototypes floating that had been tested, mainly in the Gulf of Lion, for instance. Then when you pretend to scale up that technology, then maybe the things will be more complicated because you have a larger infrastructure that needs to be not only have maintenance, but also to consider, let's say, large scale impacts. Okay, and that, again, we will see that when happens if there is some infrastructures that are put in place, for instance, in the Mediterranean or in the Atlantic, let's say put a wind farm of 80 windmills and see what happens when there are high energy storms. So I think that we can assess something by models, but it's only in the modeling stage. So there is, as far as I know, there is not so much information on that. But the idea is that, my idea is that we should be not only for the environmental impacts very cautious, but also because, as we know, due to the climate change, the intensity and the frequency of the storms and high energy events will increase in time. So that makes that the assessment should be take into account that. And as far as I know, there is no so much literature on that side.
Well, there are studies on the, for instance, there was a study on the increase in the resource of ocean thermal gradients that is expected to increase due to increase in the average temperature of the ocean. And there were other studies also that looked at the impacts of climate change. But yeah, so that's basically it. Thank you, Jordi.
Thank you for this talk. Looking at one of the final figures that you show, especially the one that it's broken with the scales, no? These logarithmic scales, one have the idea, and the image from this figure is that we have to go to offshore winds, no? That doesn't make sense to really invest, or perhaps only locally and regionally you can invest in other things, but this is the way to go, no? That's the message from the talk?
Actually, this is what we get also. This is the idea that we get, that 90% of the potential, of the technical potential, corresponds to offshore, so offshore wind. And the rest, they may be interesting in certain regions. For instance, tides, the potential of tides may be used in these specific, very specific regions, or in Canada, or in the UK, or in these specific areas. Waves are a bit more everywhere, let's say, so they could be used a bit more everywhere, but yeah, in terms of the gross potential, how much, in terms of proportion, offshore wind is like the king without doubt.
And I have a second question also related to this image, because then the thermal, the second one, it's supposed to pump water from the deep ocean to a place which is close to the coast to make these machines to work. So does it make sense at the end? I mean, especially with this volume of water that you mentioned that it was needed. I don't think it's an alternative, no?
Yes, good point, yes. So far, it doesn't make much sense in terms of efficiency, infrastructure, and so on. But maybe in the future, this technology could be a thing, but also only in certain regions where the potentials are the highest, because otherwise, of course, in the Mediterranean, we could not do something like this because there are not these gradients persistent during the year. So, yeah. I mean, it exists and the literature is available, but for now, they, you know, it's, yeah.
Yeah, if I can add something.
Yeah, sure.
I think that we are, and particularly looking at the literature, we are raising up the wrong question, which is, it's the logic of the current socioeconomy, which is, we need energy, how we can get that energy, which we should think in another way, which is, for what we need that energy. And so, for what purpose, and if society really needs that, and where it needs, okay? So if we think in that different system, that it's, let's say, more ecosystem-based approach, then maybe we can exploit some of that energy, but not at the scale that is estimated. For instance, in an island that needs some amount of electric energy, and let's say a second world island, right? Then we can put some small electric stations based in marine energy, because there are potential there to exploit that with low environmental impact. So in that way we can explore technologies, but not at the way that we are supposing to do. So there is no a good technology in that way. It's the other way around. Okay.
Sorry, ho dic en anglès o...? Vale. Al final aquest paper el que hem mirat és la literatura de potencials globals. Òbviament si anem a mirar estudis regionals o ens haguéssim centrat en una zona en concret, els resultats podrien ser diferents, però en aquest cas estem mirant el global. Clar, amb l'offshore el potencial és immens, però això és comptant que tota la plataforma, o sigui amb un low occupation, però igualment que tota la zona que podria ser ocupada està ocupada. O sigui, clar, és un potencial tècnic perquè té en compte profunditats i té en compte les tecnologies que existeixen, però al final, segons la meva perspectiva, té molta base, és un potencial gairebé teòric, tot i que tingui en compte restriccions tècniques, perquè òbviament no omplirem tota la plataforma continental de molins de vent.
En el paper ja ho especifiquem més clarament, no? Ja fem aquesta puntualització, aquí potser no l'he fet prou clara, però sí, l'anàlisi aquest és una anàlisi que hem fet top-down, és a dir, hem mirat els globals, valors globals del potencial, mentre que per fer-ho bé, diguéssim, si hi haguessin les dades, que per això no ho hem fet, seria de fer-ho al revés, d'analitzar cada lloc específic on es podria estudiar, on es podria produir aquesta energia, fer la suma fins a obtenir el global. Però realment és que no hi ha dades per fer-ho. Per això hem fet l'alternativa, que és fer-ho de dalt a baix.
Hi, just a curious question. Have you come across your study because you studied the energies, the different technologies separately, have you come across any combination of those? Because it would logically increase the ROI.
Yes, that's a point that thank you for the question, it's a very good point. This we explain it in the paper. For instance, for OTEC, it can be used also to desalinate water in combination, and then it brings additional benefits, not only energy per se, but also additional benefits, which and also they mentioned for more controlled conditions for aquaculture and all these sort of things. So it has a low efficiency, but it's true that combined with other technologies or for other purposes, the efficiency of the overall system may increase. And the same for instance, offshore wind and on wave energy, or these sort of combinations. Yeah.
Thank you for the talk, very interesting. Then I have a question related to the environmental impacts. So when you went through all this literature about the different methods, how rich or limited is the literature about the environmental impacts of each one of those techniques? Because I imagine that everyone, when it was put into this scene, so there was some voices also raising the cautious, this precautionary principle. So what did you find?
Actually, when using this top-down approach, or looking for global potentials, of course, there's less consideration of the environmental impacts, because environmental impacts are very local. So they do not tend to include this for this reason. But in the Medeas project, which was led by Jordi, and I worked here in this project, there we analyzed, we made a literature review about the environmental impacts of marine technologies, and part of it has ended up in this paper, but very small part. And yeah, it was fun that the first problem is that there's no baseline indicators for biodiversity, the potential biodiversity effects. So there's, in some areas, we still don't know what lives there, so we don't have the baseline. That's one of the problems. And then, of course, we need cables to transmit the energy from offshore to onshore. These move in the bottom. They also generate electromagnetic fields which affect the fauna. They also need boats, and the boats have their effects. They also mobilize sediments at the bottom of the ocean, which is also another impact. So there are plenty of impacts that really need to be assessed before we can deploy these technologies in large scale in a safe way, I'd say. I don't know if I answered your question.
Yes, well, I was curious about offshore wind by default, but I was curious also about the other systems, in the sense that what did we learn from all those systems that are reached or were proposed before offshore wind, and how it was made? So are there lessons learned from the other systems? So we need enough tools to say the precautionary principle, how it should be implemented, or it is to move forward, no? In the sense, are lessons learned from the others as well. It's to complement.
Yeah, well, as I mentioned, there's this literature review, and they mention these impacts, but there's no. I don't know how to summarize everything into a sentence, but yeah. So there are plenty of impacts, and so we need to approach it very, very carefully. Otherwise, we risk making more damage than the benefit that they may bring. So, I don't know if any of the co-authors may add something else. Jordi, you want to add
Thank
something?
you.
Yeah, just a comment about that. The problem is that we don't have a standard methodology. That's the problem, in the question that you pointed out, right? So, because the environmental impacts and the ecosystem impacts are so diverse, and so it's strongly place dependent somehow, then there is no a general methodology, at least in the bibliography. I think that's point one. Point two is that studies are more focused, and more interest from the industry side point of view, not from the environmental protection point of view. So that explains why there is not so large methodology or so standard methodology to assess that impacts. It's my point of view, right? So
yeah, and actually to complement that, in the papers that we reviewed for life cycle assessment studies, they mentioned that there's not even a standard methodology to evaluate the impacts, because they're not yet known, the impacts that may be produced. So, yeah.
So in Europe, we will have a problem. Just to say, because it's my neighbor, no? It's zero. Then we have a problem.
yeah, so in fact we have a problem because we don't have a methodology to properly assess the environmental impacts of that technologies at sea. Yeah, that's the point. Yeah.
A mi m'ha semblat interessant com a referència així del mundo mundial, però em dóna la impressió que comencem una mica la casa per la teulada. No sé com es diu això en anglès, però deu tenir. I veient els números que surten, em sorprèn bastant la disparitat que hi ha de números amb diferents tecnologies. O sigui, em sembla que, tenint en compte que es tracta d'una cosa que és com molt global i molt així fora del món real, em costa una mica d'entendre per què hi ha aquestes diferències, que m'ha semblat a mi que hi eren diferències bastant grans i m'agradaria saber per què. Però no per què en cada cas, sinó així, què opineu d'aquestes diferències que surten. I per últim, un comentari només, és que el que deia a començar la casa per la teulada és que De fet, aquestes coses normalment el que es fa és començar-les al revés, i començar la casa amb els fonaments. I per això el tidal, l'energia mareal, s'ha fet amb un parell de punts, ja s'ha vist que va l'assumpte i han dit que vale, que d'acord, que ja ens ho farem mirar. Però lo del vent ha sortit dels pals aquests clavats en el fons, però esteu parlant de la tecnologia aquesta que flota, que és la que ens venen ara com si fos la meravella última del món, i m'ha cridat l'atenció que mencionessis que hi havia estructures d'aquestes fondejades a 2.000 metres. És veritat?
Encara no hi són.
Ni hi seran.
No, però l'Agència Internacional de l'Energia és el que planteja, que puguin arribar fins a 2.000 metres.
I la pregunta és, aquesta gent on viuen? Perdó, no pregunto.
És una molt bona pregunta.
Pregunto, perquè és que jo no em puc imaginar un catxarro fondejat a 1.000 metres de fondària. O sigui, només el gruix de les cadenes involucren pràcticament tot l'acer que es pot fabricar en un any en el món mundial. Així fent 4 números. I llavors, i a més això com ho mantens allí amb una ventada, com alguns llocs dels que surten aquí que són amb vents espantosos. Vull dir, jo entenc que una estructura la pots clavar i mira, allò, si t'assegures que quedi ben clavat, aguantarà el vent. Però una cosa que floti, amb unes cadenes normaletes, diguem, no sé, heu fondejat alguna vegada en un lloc, amb un barco, amb un superpetroler a 2.000 metres de fondària? No ho entenc, sincerament. Però per aconseguir subvencions europees sí que va bé.
Sí, és un molt bon punt. De fet, no sé si heu notat el meu to irònic quan he comentat aquests valors més grans, però directament aquí, en el resum, diguéssim, ja directament hem posat un valor una mica més raonable i en aquest cas anava fins a 50 metres de profunditat per ara, fins a 50, que és el que podem fer ara. I es pot anar una mica més enllà, hi ha plataformes fins a, si no m'equivoco, uns 200 metres, però tampoc ens hem cregut els valors més grans, els hem descartat. Llavors, pel que dius que comencem la casa per la teulada és el que comentava abans, que hem fet un estudi top-down. Diguéssim, idealment ho hauríem de fer al revés. El problema és que per fer-ho al revés, primera que no era l'objectiu del nostre treball, perquè és a dir, nosaltres el que preteníem era poder donar uns valors que es poguessin introduir en aquest model que fem servir en el projecte Locomotion i per tant ens interessava el potencial global. Llavors ens vam basar exclusivament en les avaluacions a nivell global. Evidentment, per fer-ho bé, com he comentat abans, s'hauria de fer al revés, començar mirant lloc per lloc quina tecnologia seria la més convenient, perquè a vegades no només pot ser una, sinó que poden ser diverses, i fer al revés, construir aquest potencial global de baix cap a dalt. Aquesta seria la idea. I llavors, respecte a l'altra pregunta d'aquests rangs de valors, que també ens xoca a nosaltres i que ho discutim en el paper, al final hi ha diversos factors. Un és les metodologies que s'han utilitzat per cada estudi. Hi ha estudis que utilitzen rules of thumb, no sé com es diu en català, i d'altres que utilitzen models molt sofisticats, etc. Vull dir que hi ha metodologies molt diferents. Després també es fan, com he comentat amb offshore wind, hi ha hipòtesis molt diferents perquè encara es desconeix, hi ha un desconeixement bastant important, perquè tampoc s'han explotat a gran escala. Llavors, moltes coses que potencialment poden afectar la producció d'energia en aquests sistemes encara no se sap. Per exemple, el que comentava de l'estudi de l'Antonio García Olivares, que ell considerava de forma conservadora un watt per metre quadrat, mentre que altres estudis consideren 5 watts per metre quadrat o 7. Llavors, és clar que depèn molt de les hipòtesis i per això també a les conclusions comento el punt 5, o el punt 6, perdó, que hi ha una incertesa bastant important i que nosaltres només hem donat ordres de magnitud i que, evidentment, cal molta més recerca en aquest sentit. Però, diguéssim, com que aquestes dades al final són necessàries, perquè s'han de treure a algun lloc, doncs aquest és un primer estudi en el qual hem mirat de fer una quantificació a grans trets de quins són aquests potencials.
Sense entrar en detall dels estudis, però a vegades dona la impressió una mica que alguns d'aquests estudis que heu dit potser estan fets sobre la base aquella de dir aquests són els meus principis, però si no li agraden, canvio un, no?
Sí, totalment, no? I depèn de... A veure, això eren tots estudis científics, però clar, qui financia aquests estudis científics tampoc hem entrat aquí a mirar, no? Però bé, i de fet és una cosa que ens va xocar molt, no? Inicialment, quan vam començar a mirar la literatura, hi havia, per exemple, d'energia de les onades d'1 a 10 terawatts de rang, no? Que llavors vas explorant i vas veient, no? Qui és que diu una cosa, qui és que diu l'altra, no? Llavors nosaltres hem donat, i nosaltres segurament hi haurà molta gent que ens acusarà de pessimistes, mirant els resultats que donem nosaltres, no? Però nosaltres pensem que és tot el contrari, que hem sigut molt optimistes a l'hora de buscar la literatura, o sigui, no molt optimistes, però que diguéssim que no ens hem cregut els valors aquests més poc creïbles, no? Vull dir, i que una de les coses que volíem fer amb aquest estudi era això, no? Limitar aquests rangs, no? Perquè són rangs de valors que es repeteixen en la literatura una i altra vegada, no? Quan mires les revisions bibliogràfiques, contínuament, doncs això, entre 1 i 10 terawatts, no? I bueno, per algun lloc algú s'està equivocant, no? I la idea una mica era estrènyer aquest rang, no? I fer-ho una mica més digerible, no? I reduir una mica aquesta incertesa, que ho hem fet millor o pitjor, ja és discutible, però bueno, almenys ho hem intentat. Però sí, totalment, tota la raó.
Hola, el tema del material ha sortit abans, no? Però d'on traiem tot el material necessari per construir tots aquests trastos? Vull dir, hi ha un informe del govern canadenc que a partir del 2030 tindrem seriosos problemes d'abastiment de coure.
Mira.
I aquest és dels elements que més n'hi ha en superfície. O sigui, ja ni et dic anar a les terres rares per construir els generadors.
És un excel·lent punt. Aquest trasto d'aquí, que s'utilitza, bueno, que està en fase de prova al Japó, si no m'equivoco, la idea d'aquest és aprofitar les corrents oceàniques per produir energia. Aquest trasto d'aquí, que s'ancla al fons del mar i està circulant aquí a uns 50 metres de profunditat, que ja no et dic els impactes a la fauna marina, etc. Aquest trasto pesa 300 tones. Per tenir una idea de la magnitud, no, de la tragèdia, és un molt bon punt, és a dir, d'on es trauran tots aquests materials? I d'on es trauran per produir plaques solars i tot, no? Vull dir, sí, tenim un problema en aquest sentit i hi ha molts estudis que fins i tot n'hi ha que diuen que la transició energètica no és possible. Però aquí nosaltres no entrem perquè tampoc era el tema d'aquest treball, però sí, difícilment es podrà... També com deia el Jordi, que la idea tampoc ha de ser anem a explotar tot el recurs disponible, no? Ha de ser utilitzem el recurs que realment sigui necessari per mantenir unes condicions de vida decents, no? És a dir, és clar que amb el sistema de vida que portem actualment, i això és un altre tema completament a part, no podem continuar amb aquest sistema de creixement continu perquè els recursos són els que són. Però potser, no, si anem una mica més avall i acceptem unes condicions de vida una mica menys ostentoses que les que tenim actualment, doncs probablement es pugui minimitzar també la necessitat de recursos, etc. I fer una cosa que encaixi i que ens permeti viure de manera digna. Gràcies per la pregunta.
Una puntualització també sobre això.
L'esperava.
Que a banda, això ara ho acabem de comentar amb en Jordi Salat, que si anem a pensar una mica això, o sigui, tu has dit que això feia aquest aparell
300 tones fa 20 metres per 20 metres
per donar 100 quilowatts. O sigui, tenim una massa...
És una mica com l'OTEC, al final.
Per això hem descartat l'Ocean Forever.
I llavors, també en la direcció aquesta una cosa és això i l'altra és que, diguem-ne, el que no s'admet públicament, però el que està darrere de tots aquests estudis és que ja se sap que no hi ha prou materials per portar això a terme. Ni això, ni el desenvolupament renovable, perquè, a veure, alguns resultats que tenim recents del model PAEMDEAS ens diuen que, per exemple, si fem un 100% renovable, esgotem, o sigui, necessitem el doble de les reserves provades que hi ha, per exemple, de plata, o de coure, o de neodimi, etc. Llavors, això ja se sap. La cosa és que aquí hi ha una qüestió de que primer s'ha de fer l'anàlisi teòric per veure que això realment no pot ser ni tan sols a nivell teòric. I després, a partir d'aquí, llavors mirem com organitzem les coses d'una manera diferent, que és el que s'haurà d'acabar fent. És a dir, ara estem en l'època aquesta encara del Green Deal i del Green Growth, etc., però això té el recorregut que té.
Per no parlar que l'energia que s'utilitza per fer aquest tipus de dispositius és d'origen fòssil, que afegeix encara més complexitat a l'assumpte. Com ho farem quan només tinguem l'energia renovable?
Més preguntes? Sí? Doncs, jo crec que si no hi ha més preguntes i amb el vistiplau del Ramon, ho deixem aquí. Moltes gràcies.
Moltes gràcies.